Now that we've described the kind of overall process and goal of what we're trying to achieve with regard to hypothesis testing, I want to go through the individual steps that you need to do in order to conduct a hypothesis test. Then we'll specifically talk about how to apply that framework to large and small samples. And within each of those, we're going to have a couple of different examples. So to begin, the first step is that we have a number of assumptions that we need to make about the data. And more specifically, about where the data generating process is coming from. And by that, I mean, are we getting this data from an experiment in the sense that there's a treatment that is randomly allocated to individuals? Are we receiving this data as observational data where there is no active intervention and it's just passive collection of information? These are things that are going to influence how we go about analyzing the data and whether or not we can even conduct a hypothesis test in the first place. So one of the first important assumptions that we have to check is what type of data do we have? Do we have continuous variables? Do we have categorical variables? We have to think about the population distributions. We have to think about the sample size. And by population distributions, I mean based on whether or not we have a categorical variable, that's going to depend or going to influence the type of distribution that we're going to invoke, right? If we have a continuous variable, we'll learn we're going to use ordinary least squares or just simple linear regression. If we have a dichotomous outcome, we may want to use a logit model. Then, like I said, we're going to have to consider the sampling method, whether or not the data generating process is random or whether there is some sort of endogeneity. And by that, I mean some sort of cyclical or self-fulfilling system within the data that if we don't correct for, that may bias our results. With all of our assumptions met, we can go ahead and actually set up our hypothesis test. The way that we're going to do this is we're going to use a technique in logic called proof by contradiction. Essentially, what we're going to do is we're going to set up a null hypothesis and hope that we find sufficient evidence to suggest that that hypothesis is unlikely. That is a little confusing, so let me describe that. In order to set up a null hypothesis, we're going to make a statement such that we think the relationship is equal to 0. There is no relationship. So if we find sufficient evidence to suggest that there is a relationship, that would overturn the null hypothesis. And we'll do this by using a sample statistic to show, again, that it's very unlikely that we would have observed the null hypothesis with this data. Now, we will be somewhat deriving a conclusion that our null hypothesis is not true. It's usually called the alternate hypothesis, but I'm going to talk about it and really emphasize careful language to always say that we either find sufficient evidence to suggest that the null hypothesis can be rejected, or we cannot find sufficient evidence to reject the null. I will very rarely say we find sufficient evidence that the alternate hypothesis is true. And again, this is mostly because of the way that we are setting this up through proof by contradiction. But before we can make any conclusion as to whether or not a hypothesis is true or not, we need to actually specify what that hypothesis is. And we're going to do that in our third step by calculating a test statistic. This test statistic is going to summarize how much of our data differs from what we would have expected to observe if the null hypothesis was true. So this is usually going to be something that's equivalent to a z or a t statistic, where we are referencing a t distribution with our t statistic to see if our statistic is something that we believe we would likely observe if the null was true. With our test statistic in hand, we can now provide some sort of calculation or measurement of surprise around that test statistic, right? So it may not be just enough to say that the typical value of a test statistic in the 95th percentile would be this, and this is what we found. It's more intuitive to say that we have passed a critical threshold such that we have found sufficient evidence, right? We need to have some bar of comparison. And essentially what we're doing is we're asking, if the null hypothesis is true, how likely is it that we would observe a test statistic this extreme or more? So smaller p-values more strongly contradict the null, right? A larger and more extreme value is going to be associated with a smaller p-value because it's farther away than what we might have expected. And I understand that this is not necessarily intuitive right away. That's okay. These are very difficult to understand, and there are many people that have advanced degrees and have taken many stats courses that could not define a p-value or a hypothesis test correctly. The important part is that we concentrate on defining it correctly and applying it in a proper manner. The final step of hypothesis testing is finally drawing a conclusion from that p-value. So we have to answer, how surprised would we be in order to conclude that the null hypothesis is false? Essentially, in other words, what is the bar that we're going to set as evidence to reject the null hypothesis? And I'm sure that you've heard this before. Usually it's called statistically significant, and this is a p-value of 0.05 or less. This is essentially saying that the test statistic falls outside the range of 95% of the test statistics we would likely encounter if this was the true data generating process. In other words, we would observe this test statistic, a test statistic this extreme or more 1 out of 20 times if our null hypothesis was true. So again, remember, we're not even saying that we're 95% certain. We're saying that if we did this 20 times, 1 out of the 20 times, the null hypothesis would actually be true if we were to reject it. So more generically, we always want to decrease our p-value, right? The lower our p-value is, the greater, I guess, certainty, or the more surprised we would be if the null hypothesis was in fact true and we rejected it. Now, if we do find a p-value that is below our critical threshold, we typically can reject the null hypothesis and conclude that the evidence supports our alternate hypothesis, though I would highly recommend against using that kind of language.